Hello everyone. Once again welcome to MPLS series. Guys, this is day 2 of traffic engineering videos. In day 1 we discussed why we come up with traffic engineering, and today in day 2 we are going to understand basic configuration and verification of MPLS traffic engineering. See, in this video we will discuss how to enable MPLS traffic engineering on routers and how to create tunnel between source and destination. But before discussing the configuration of MPLS traffic engineering, I would like to tell you about MPLS traffic engineering components, like what are the requirements of MPLS traffic engineering. So guys, MPLS traffic engineering or TE requirement is, first requirement is IGP protocol. We need one IGP protocol right, to configure MPLS traffic engineering. Okay, let's say here we have 4 routers: router 1, router 2, router 3, router 4, and router 4 is connected with one network, that is 192.168.10.0/24. And between router 1 and router 4 I want to reserve, let's say, some bandwidth, right? I want to reserve some bandwidth for a particular application. Let's say here router 1 is connected with one application. Okay, router 1 is connected with one application, and this application need 1.5 megabit per second of bandwidth between router 1 and router 4. This application need 1.5 megabit per second of bandwidth. See, 1.5 megabit per second bandwidth is available from the upper path, and here we are running OSPF routing protocol. So definitely by default router 1 will install upper path in their routing table for this destination. Getting my point? But let's say on this link and on this link there are lots of other traffics, right? There are lots of other traffic, so I want to reserve 1.5 megabit per second for this particular application. So yes, we can achieve it with the help of MPLS traffic engineering, because as you know, why we come up with MPLS traffic engineering, what is the reason? Reason is very simple. In last video also we discussed it. So that we come up with MPLS traffic engineering so that we can use bandwidth more efficiently. We can use bandwidth more efficiently, or do not need per hop routing. Like if I will talk about IP routing, so in IP routing we need per hop routing. Let's say this computer have one IP address, that is 10.1.1.1, and this 10.1.1.1 want to communicate with 192.168. let's say 10.1, right? Destination belongs to this network. So this computer will forward traffic to router number 1 to their default gateway. Router 1 will check their routing table. It will compare destination IP in the packet with routing table. After that it will forward the traffic to router number 2. Router 2 will do same thing. It will also check their routing table. It will compare the destination IP address. After that it will forward to router number 4. Router 4 will also do same thing. It will check their routing table. It will compare the destination IP address with routing table. Then it will forward the traffic to destination device. This is what? This is per hop routing. Every router is checking their routing table, right, to forward packet. But in MPLS traffic engineering we don't need per hop routing. R1 can decide the entire path, because we will have one tunnel between R1 and R4. So basically we can say MPLS traffic engineering is used to reserve bandwidth between source and destination, between head end router and tail end router. See, what is head end router and tail end router? First of all, there are two types of router in MPLS traffic engineering, guys. First one is head end router, and second one is tail end router. The first router, like router 1 is connected with one application, right? So router 1 is what? First router that receive the traffic. Router 1 is the first router that receive the traffic, or you can say the router 1 is the router that is going to calculate best path by CSPF algorithm. By CSPF means constraints shortest path algorithm, right? CSPF is an concept of OSPF. We'll discuss about this in upcoming video. For now, just understand C stands for constraints and SPF is algorithm that OSPF uses for calculating best path. So the router who is going to calculate best path by using CSPF algorithm is known as head end router. So in my scenario, router 1 is my head end router. Router 1 is my first hop router. So this router is head end router, head and router, and router 4 is the last router, right? So router 4 is my tail end router. This is tail end router, tail and router. Between head end and tail end, we want to reserve some bandwidth, like let's say 1.5 megabit per second bandwidth. I want to reserve 1.5 megabit per second bandwidth, right? So we need what? One IGP protocol to share information about the link, like let's say between router 1, router 2 and router 4, the remaining bandwidth is 1 megabit per second only, remaining bandwidth, and rest 1 megabit per second bandwidth is already reserved for other, let's say, application and for other resources, for other purpose. So here remaining bandwidth is only 1.1 megabit per second bandwidth, right? So R1 R2 need to share this information to router number 1, and router 1 have, let's say here we have again 1 megabit per second bandwidth, so they need to share with their neighbor about the remaining bandwidth. Like this we need to share some additional information about the link with the help of CSPF, with the help of CSPF, constraint SPF algorithm. So first components of traffic engineering is IGP protocol. Why IGP protocol? Why we need IGP protocol? We need IGP protocol to share constraints information about the link. So we need one IGP protocol here, and IGP protocol can be OSPF or ISIS only. It can be either OSPF or it can be ISIS protocol, because only these two routing protocols have capability to share these information of links with neighbor in the form of LSA. All right. External EIGRP or rerouting protocol cannot share this information of link with neighbor. So that's why in IGP protocol, as a IGP protocol, we can use either OSPF or ISIS. So first requirement of MPLS traffic engineering is IGP protocol. Still we need IGP protocol. First you have to configure IGP protocol between router 1, 2, 3, 4. Right? So we can use either OSPF or ISIS. In this video we are going to use OSPF protocol as a IGP protocol. Now the second components of MPLS traffic engineering is RSVP. RSVP. RSVP, as you know, RSVP stands for Resource Reservation Protocol. Resource Reservation Protocol. This protocol generally used in quality of service to provide quality of service. We are using this protocol to provide quality of service. We are using this protocol in quality of service. Here also we are going to, in MPLS traffic engineering also, we are going to use RSVP protocol to reserve bandwidth between head end and tail end router. Between source and destination router we are going to reserve bandwidth with the help of RSVP protocol. How? Because in RSVP protocol, guys, you have to understand two types of messages. In RSVP protocol there are two messages. First one is RSVP reserve path message. First one is path message, RSVP path message, and second message is RSVP reserve message. Reserve message, right? So my head end router, let's say between router 1 I want to reserve 1.5 megabit per second bandwidth between router 1 and router 4. So router 1 is my head end router, first hop router. So router 1 will send one path message to router number 2, one RSVP path message. What router 2 will do? Here bandwidth requirement is 1.5 megabit per second, let's say. R2 will put 1.5 megabit per second bandwidth on standby. If 1.5 megabit per second bandwidth is available, right, it will check outgoing interface bandwidth. If outgoing interface bandwidth, outgoing interface, this amount of bandwidth is available, it will put that amount of bandwidth on standby and it will relay that path message to router number 4. It will forward that path message to router number 4. Path message with bandwidth requirement, what bandwidth requirement is 1.5 megabit per second. Now R4 will also check their bandwidth. If bandwidth is available, R4 will reserve 1.5 megabit per second bandwidth, and R4 will send one reserve message to router number 2, RSVP reserve message. And if with the help of RSVP reserve message, R4 will also send one label. Guys, if I will talk about MPLS, so in MPLS we use LDP protocol to exchange label. If I will talk about L3 VPN, MPLS L3 VPN, so we use MPBGP to advertise label, or we are using LDP protocol to advertise label. In MPLS we use LDP, in L3 VPN we use MPBGP and LDP. But in traffic engineering, in case of MPLS traffic engineering, we are using RSVP to advertise label, right? So router 4 will send one label also with the help of reserve message. Let's say it have sent label what, pop. It will send pop label because destination is directly connected with router number 4, right? After that, router 2 will send this reserve message to router number 1, reserve message, and it will also send one label. Let's say it is sending label 200. So on router number 2, outgoing label is pop the label. On router number 1, outgoing label is 200, right? Because router 2 have advertised label 200. And this is how we can reserve 1.5 megabit per second bandwidth between R1 and R4, between R1 and R4, right? So RSVP is the requirement. Second requirement is RSVP, and the third requirement is SAF, IPSAF. But by default, as you know, SAF is running, so we don't need to run command IPSAF on router, right? If SAF is disabled, then you have to enable SAF also. So these are the components of MPLS traffic engineering. Hope it is clear to you. First of all, we need one IGP protocol, and IGP protocol can be OSPF or ISIS. And don't worry guys, we will understand about these things in detail in upcoming videos. But for now, understand only one thing, that is we need IGP protocol, and IGP protocol can be OSPF or ISIS only. Second requirement is we need RSVP protocol. We have to configure as RSVP protocol to enable traffic engineering. We have to use this protocol. In this protocol we have two types of message. One is path message, one is reserve message. My hidden router will send one path message to neighbor router. Neighbor router will, if neighbor router is not the tail end router, it will send that path message to other neighbor, and it will put that bandwidth on a standby. And when router 2 will receive reserve message from router number 4, it will also reserve 1.5 megabit per second bandwidth, right? This is how it is going to work. Now just try to understand the basic configuration for now, then in upcoming day slowly we will understand everything, and gradually we will move, right? And at the end you will become master in traffic engineering. So now here I have topology. Here you can see I have topology. First, I have already configured the IP address on all routers. Like on router number 1, if you want to see IP, so IP interface brief exclude unassign. See, we have one IP address on physical interface fast Ethernet 0/0, that is 12.1.1.2.1, and on fast Ethernet 1/0 13.1.1.1. And I have created one loopback where I am running IP 1.1.1.1. Fine. So let me show you the R2 IP configuration. Let me close this paint because now we don't need this one. On router number 2 also you can see IP configuration. So IP interface brief exclude unassign. Here also on fast Ethernet 0/0 IP is 12.2, on fast Ethernet 1/0 IP is 24.2, and I have one loopback where I am running 2.2.2. Fine. On router number 3 also, let me verify the IP configuration. Enable, and so IP interface brief exclude unassign. So IP interface brief exclude unassign. So here I have one IP address on fast Ethernet 0/0. I have one IP address on fast Ethernet 1/0, and I have one loopback. And finally, on router number 4, you can see the IP configuration. Let me check, verify. So IP interface brief, exclude, unassign. So here also on fast Ethernet 0/0, I have this IP address, on fast Ethernet 1/0 this IP address, and we have two loopback. One is 4.4.4 and one is my this network 192.168.10.0/24 network. Let's say this is one LAN connected with router number 4. Now let me start the configuration from IGP protocol. First of all, we need to configure IGP protocol. So IP protocol, you can see here I don't have any IGP protocol. So let me configure OSPF here. Router OSPF process ID 1, let's say router ID 1.1.1, exit interface range F0/0, F1/0, and loopback 1. I'm going to say IP OSPF 1 area 0. Done. So IP OSPF interface brief, you can see OSPF is enabled on all interfaces. Now I am going to configure OSPF on router number 2. Config T router OSPF 1, say router ID 2.2.2.2, and exit interface fast Ethernet 0/0, fast Ethernet 1/0, and loopback 1, IP OSPF 1 area 0. Interface range is missing, na? range and IP OSPF 1 area 0. Done. Soon OSPF neighborship will come up between router 1 and router 2. Till then, let me configure OSPF on router number 3. Router OSPF 1, router ID 3.3.3. set router OSPF 1, router ID 3.3.3.3, exit interface range F0/0, F1/0, and loopback 1, say IP OSPF 1 area 0. Done. Okay, now on router number 4, and let me check the neighborship. Yes, we have neighborship, right? OSPF neighborship. Finally, let me configure OSPF on router number 4. So router OSPF 1, router ID 4.4.4.4, and exit interface range F0/0, F0/0, F1/0, and loopback 1. I am not advertising this network 192.168.10.0/24 in OSPF. Let's say IP OSPF 1 area 0. Now on router number 1, we can check the routing table. Router 1 routing table. So IP route OSPF. So yes, it is receiving, it is not receiving 4.4.4. Just wait for some time. OSPF neighborship is not up, I think, between router 2, 4 and between router 3 and router 4. Let me check R4. Here we have OSPF neighborship with router 2, and soon OSPF neighborship will come up with router number 3 also. So IP OSPF interface brief, OSPF is enabled on yes. Now we can verify the routing table of R1, and yes, R1 is receiving 4.4.4 from both path. It is performing load balancing. As you know why it is performing load balancing, because I have not configured the bandwidth. So by default bandwidth is same, because we are using same link, fast Ethernet link. So I am going to say fast Ethernet 0/0 interface, fast Ethernet 0/0. Here I am going to set bandwidth 2 megabit per second, and on fast Ethernet 1/0 interface fast Ethernet 1/0. Here I am going to set bandwidth 1 megabit per second. Done. And now on router number 2 also, let me set the bandwidth. On router number 2 interface range F0/0 and F1/0, I'm going to say bandwidth is 2 megabit per second. Done. On router number 3, both interface will have 1 megabit per second bandwidth. Interface range F0/0 and F1/0. Here I am going to say bandwidth 1 megabit per second. Fine. And finally on router number 4, config T interface fast Ethernet 0/0. Here bandwidth is going to be 2 megabit per second, and on fast Ethernet 1/0 bandwidth is going to be 1 megabit per second. Fine. Now if you will verify routing table of R1, now you can see it is not performing, R1 is not performing load balancing. So IP route OSPF for 4.4.4 best path is via router number 2, because upper path have more bandwidth, so it will calculate less cost, lower cost as compared to lower path. So upper path have lower cost, so that's why upper path is the best path for 4.4.4. Now let me enable MPLS on this router. How to enable MPLS? See guys, I am not going to configure tunnel now. First we need to enable this feature, MPLS traffic engineering feature, on all routers, and we need to enable MPLS traffic engineering globally also, in global configure terminal mode also, means globally, and you have to enable it on interfaces mode also. Okay, so we need to run this command MPLS traffic engineering tunnel on global config mode also and on interface mode also, right? This is the command to enable MPLS traffic engineering. This is MPLS traffic ENG, not engineering, ENG tunnels. This command will enable MPLS traffic engineering on router. Okay, so here before configuring MPLS traffic engineering, I am going to say MPLS label range. Let's say here I am going to say label range is 100 to 199, and then I am going to say MPLS traffic engineering tunnel, this command, and this command will enable MPLS traffic engineering globally. And you have to run this command on interface also, interface fast ethernet 0/0, and we can use range command, interface range fast ethernet 0/0 and fast ethernet 1/0. Here I am going to say MPLS traffic engineering tunnels, right? Interface mode, interface basis, and then we need to run this command IP RSVP bandwidth. IP RSVP bandwidth, the purpose of this tunnel, right? Let me hit enter, and now see, after running this command, I have run this command on both interface. If I will run this command, so IP RSVP interface, see interface here on fast ethernet 0/0 RSVP is enabled, and the maximum reservable bandwidth is 1500 kilobyte, only 1500 kilobyte. Why? We have 2 megabit per second bandwidth here, means 2000 kilobyte. Then why we can reserve up to 1500 kilobyte only? This is maximum reservable bandwidth, means you can reserve up to 1500 kilobyte bandwidth on fast ethernet 0/0, and you can reserve 750 kilobytes bandwidth on fast ethernet 1/0, right? Because in some iOS by default, if you are not defining the bandwidth, if you are not defining the RSVP bandwidth, it will take 75% bandwidth from the configured bandwidth. So configured bandwidth is 2000 megabit per second. It is taking 75% of 2000 megabit per second is 1500 kilobyte. So we can reserve up to 1500 kilobytes bandwidth only, 1500 kilobyte bandwidth only. But if you want to utilize all bandwidth, you want to reserve all bandwidth, so you can define here bandwidth, right? I can run this command IP RSVP bandwidth and then 2000, but I am using range command, so I cannot use this command because this amount of bandwidth is not available on fast ethernet 1/0. So here what I am going to do, I am going to run this command manually on interface. Let's say interface fast ethernet 0/0. Here I am going to say IP RSVP bandwidth is 2000 kilobyte per second, and now do so IP RSVP interface. Now you can see on fast ethernet 0/0 maximum reservable bandwidth is 2 megabit per second, means 2000 kilobyte. So if you will not define this bandwidth, if you are simply running this command IP RSVP bandwidth, it will reserve up to 75% bandwidth, and if you want to reserve all bandwidth, you can configure the bandwidth value, right? In the same way on fast Ethernet 1/0 also, I want to utilize all bandwidth, so I can run this command IP RSVP bandwidth and 1000 kbps here. And now if you will verify to show IP RSVP interface, you can see on fast Ethernet 0/0 we can reserve up to 2 megabit per second, 2 megabit per second, and on fast Ethernet 1/0 we can reserve up to 1 megabit per second, but allocated bandwidth is 0. Now we have not reserved any bandwidth, right? This is the maximum value which we can reserve here. Fine. So here we have run enable MPLS traffic engineering globally also, and interfaces mode also, and now we need to run some command in OSPF mode. OSPF mode, here we need to run some command in OSPF mode like router OSPF and process ID was 1. Here also I am going to say MPLS traffic engineering router ID. Router ID is pick router ID from the loopback 1 interface, right? From the loopback 1 interface. Here see, you know, on loopback 1 interface I am running what IP 1.1.1.1. so MPLS OSPF MPLS router ID is going to be 1.1.1.1, and then MPLS traffic engineering area ID is 0. That's it. These are the command to enable MPLS traffic engineering on router number 1. Now MPLS traffic engineering is enabled. Over here this is basic configuration, this is not tunnel configuration, right? This is initial configuration. These are the configuration, these are the initial configuration that we should configure it on router if we want to use MPLS traffic engineering. Fine. Now second step is we need to run these all command on all other router also. And if you will check one thing here, so IP OSPF database, inside the OSPF database you are able to see LSA 10 now. LSA 10, opaque LSA. As I told you, until and unless you will not enable MPLS traffic engineering, you know, you will not experience this LSA. LSA 10, that is opaque LSA. You will have LSA 1 router LSA, you will have LSA 2 because we are using broadcast link, so we have this, what we say, LSA 2 network LSA because of DR and BDR, and then we, because of MPLS traffic engineering, we have this LSA 10, that is opaque LSA. Fine. Now here let me do one thing on router number 1, interface range F0/0 and F1/0. I am going to change OSPF network type also. So IP OSPF network point to point, because network type should be here point to point, na? So I have changed the network type. Now I am going to take you to router number 2. On router number 2, here if you will, first of all let me change the network type, interface range F0/0 and F1/0, IP OSPF network point to point. And now here if you will check, so IP OSPF database, so see opaque LSA, right? Here we have not enabled MPLS, but router 1 have advertised this opaque LSA. Advertiser router ID is 1.1.1.1, right? Because on router number 1 we are running MPLS traffic engineering. Okay, so what we are going to do now, on router number 2 I am going to enable MPLS traffic engineering. So first command should be MPLS label range, let me set 200 to 299, then MPLS traffic engineering tunnels, that's it. Then interface range F0/0 and F1/0. Here I am going to say MPLS traffic engineering tunnels and IP RSVP bandwidth. Let's say if I will not define bandwidth, reservable bandwidth will be 75% of actual bandwidth. So I am defining this bandwidth. Then router OSPF 1 and MPLS traffic engineering router ID loopback 1 and MPLS traffic engineering area ID is 0. For now I am configuring area 0 only. In upcoming day we will understand other area configuration also. First of all we need to understand the basic configuration. Fine. Now on router number 2, and if you will check here one command, so IP RSVP interface. So interface fast Ethernet 0/0, you can see RSVP is enabled and reservable bandwidth is 2 megabit per second on both interfaces, right? Allocated bandwidth is 00. Fine. And so IP OSPF database. In OSPF database we are able to see now opaque LSA of router 1 and router 2. Both router are advertising opaque LSA. 2.2.2 also and 1.1.1 also. Now let me take you to R3. First of all, I am going to change OSPF network type here. Interface range F0/0 and F1/0. Going to say IP OSPF network point to point, right? Then MPLS MPLS label range first. Label range is 300 to 399, and after that MPLS traffic engineering tunnel. Then interface range F0/0 and F1/0, MPLS traffic engineering tunnels, and IP RSVP bandwidth is 1000 kilobyte per second. Then router OSPF 1 and MPLS traffic engineering router ID loopback 1 and MPLS traffic engineering area 0. And now if you will check, so IP RSVP interface, so here you can see reservable bandwidth is 1 megabit per second on both interfaces and RSVP is enabled on both interface. Done. Now so IP OSPF database. In the database now you can see router 3 is also advertising opaque LSA 10. Fine. Finally let me take you to R4, and on R4 now we are going to configure MPLS traffic engineering. Interface range fast Ethernet 0/0 and fast Ethernet 1/0, IP OSPF network point to point, and then MPLS label range is 400 to 499, let's say, and then MPLS traffic engineering tunnels, then interface fast Ethernet fast Ethernet 0/0, MPLS traffic engineering tunnels, and IP RSVP bandwidth is 2000 kilobyte per second. Fine. Then fast Ethernet 1/0, and here MPLS traffic engineering tunnels, and then IP RSVP bandwidth is 1000 kilobyte per second, and router OSPF 1 MPLS traffic engineering router ID loopback 1 and MPLS traffic engineering area 0. Done. Now all routers are advertising opaque LSA 10. So IP RSVP interfaces, first verification command, fast Ethernet 0/0, reservable bandwidth is 2 megabit per second. On fast Ethernet 1/0, reservable bandwidth is 1 megabit per second. Fine. And so IP OSPF database. Inside the OSPF database we are able to see LSA 1, that is fine, and then LSA 10 opaque LSA, and you can see all routers are advertising opaque LSA. So this is basic configuration. Till now just we have enabled MPLS traffic engineering on these routers. Fine. Now what I will do, I am going to create now tunnel. See how I will create tunnel. Now I don't need to configure anything on router number 2, router number 3, router number 4. I am going to configure router number 1 only. See, on between router 1 and router 4, let's say I want to reserve 1200 kilobyte bandwidth. Let me tell you here, I am going to reserve, let's say What happened? It's not working. I'm going to create one tunnel here. Let's say tunnel 0, and tunnel 0 will have, I am going to reserve bandwidth of, let's say, 1200 kilobyte per second. Okay, so what I will do on router number 1, simply I will run some command. See, interface, first I will create the tunnel. So interface tunnel 0, like GRE tunnel, as you know how to configure GRE tunnel, interface tunnel 0, and then we need to assign one IP address on this tunnel interface. So either you can configure the IP address here, or you can run this command, IP unnumbered, and then we can say loopback 1. It will take IP address from loopback 1 interface, or if you want to configure here, you can configure the IP address also, fine. Then I can say tunnel destination. As you know, I need to define tunnel destination. So my tunnel destination is 4.4.4.4, means router 4 loopback interface. Destination is 4.4.4.4. Then tunnel mode, as you know, this is exactly similar configuration like GRE tunnel. Tunnel mode is MPLS traffic engineering. So tunnel mode is MPLS traffic engineering, and then tunnel MPLS. Purpose of this tunnel is bandwidth reservation. So MPLS, tunnel MPLS traffic engineering, and then bandwidth. Then the amount of bandwidth you want to reserve. So I want to reserve 1200 kilobyte per second of bandwidth, right? So that's it. And then we'll discuss about this command, guys, don't worry. Tunnel MPLS traffic engineering, and then path option is, let's say, 1 and dynamic, right? I want to use path dynamically, that's why I have run this command. We'll understand it later. Now see how to verify the tunnel. So MPLS traffic engineering tunnels, this is the command. Okay, so here on this router I have run this command. So MPLS traffic engineering tunnel, see the output. First of all, let me maximize it. I have one tunnel whose tunnel name is R1T0. Tunnel name is R1T0, and tunnel destination is 4.4.4.4. That is fine. Status of this tunnel is administratively up, operational up, path is valid, signaling is connected, means tunnel is working fine. Path option 1, type is dynamic, which we have configured, and then configure parameter. Bandwidth requirement is 1200 kilobyte per second, and priority, these things we'll discuss it. Metric type is traffic engineering. Fine, everything till here is okay. Now let me show you the more information. Here inbound label is nothing, outbound label is, in label is 0, nothing, out label is 200. Who have advertised this label? Router number 2, because on router number 2 only we have defined this label range. So router 2 have advertised this label. And next hop is 12.1.1.2. This is the IP address of router 2. RSVP signaling information. Source is 1.1.1. Destination is 4.4.4. Tunnel ID is 0. And tunnel instance is 1. And path, RSVP path information. My address is 12.1.1.1, and this is the exact path, right? This is the exact path. Explicit route is going to be from 12.1.1.2, IP address of router 2, then outgoing interface of router 2, receiving interface of router 4, 24.1.1.4, and then destination 4.4.4, right? So this is the path. We'll understand about this also in upcoming day, but for now this is tunnel. We have one tunnel, that is tunnel 0, and on this tunnel we have reserved 1200 kilobyte bandwidth, right? And if you will run this command, on router number 2, let's say on router number 2 I am running this command. So MPLS traffic engineering tunnels. So here you can see tunnel tunnel name is R1, tunnel 0 is signaling connected up, inbound in label is in label on fast Ethernet 0/0. Fast Ethernet 0/0 is connected with router number 1. So it is actually advertising this label from fast Ethernet 0/0. Pre hope is 12.1.1.1. We'll discuss about it, and you can see auth label is fast Ethernet 1/0 implicit null. So R4 is advertising what label? Null. Right. Next hop is 24.1.1.4 router 4, and this is the path. Right. On any router we can identify the path. What is the path? Right. And we'll discuss more about this path. Now here we have one tunnel between router 1 and router 4. Between 1.1.1 and 4.4.4 we have one tunnel. On this tunnel we have reserved 1200 kilobyte bandwidth. Right. Now I am going to create one more tunnel. Let's say here I am going to create tunnel 1, and tunnel 1 have, let's say, bandwidth requirement of tunnel 1 is 900 kilobyte. Now guys, see, when I reserve 1200 kilobyte per second bandwidth between router 1 and router 4, router 1 automatically use upper path. This is intelligence of traffic engineering, right? It have used upper path automatically. Now how many remaining bandwidth we have on upper path? Means between router 1 and router 2, how many remaining bandwidth is there? Remaining bandwidth between router 1 and router 2 is 800 kilobyte. 800 kilobyte. So, and between router 2 and router 4 also we have 800 kilobyte remaining bandwidth. So if I will create one more tunnel with bandwidth requirement of 900, router 1 will choose lower path. Let me show you here. On router number 1, on lower router number 1, I'm going to say interface, let's say tunnel, this time tunnel 1, and then IP and number loopback 1, IP and number loopback 1. Tunnel destination is same. Tunnel destination is 4.4.4.4, and tunnel mode is MPLS traffic engineering. Then tunnel MPLS traffic engineering bandwidth. So here bandwidth requirement is 900 kilobyte per second, and then tunnel MPLS traffic engineering and path option 1 dynamic. Done. Now so MPLS traffic engineering tunnel. Right. Now let me maximize it. See, we have two tunnel. First is name of first tunnel is this one. Here we have reserved 1200 kilobyte per second. My another tunnel is R1 T1, and this tunnel is down now. You have to wait for some time. So after some time this tunnel will also come up. Here I have configured 9000 bandwidth, right? So this tunnel will not come up. Why this tunnel will not come up? Because we don't have this amount of bandwidth between R1 and R4. So let me change it. Do so run what we can say interface tunnel 1. So this is running configuration of tunnel 1. I am going to remove this command, interface tunnel 1. I'm going to say no to this command, and then I am going to say tunnel MPLS traffic engineering bandwidth is bandwidth is 900. Done. Now so MPLS traffic engineering tunnels. See, this time this tunnel will come up or not. This tunnel will come up, yes. Administratively up, operational up, path is valid, signal connected, right? Everything is fine. And here we have reserved how many bandwidth, how much bandwidth? 900 kilobyte per second. So see, from the upper path 900 kilobyte per second is not available. So next hop is what? 13.1.1.3, and this time you can see source 1.1.1, destination 4.4.4, and explicit route is 13.1.1.3, means router 3. This is the IP address of router 4, right? So it have chosen lower path this time. Lower path, this path means via router number 3. And let's say here I will create one more tunnel. Let's say tunnel let's say 2, and here I am going to define bandwidth of, let's say, 2000 kilobyte or 200 kilobyte. If I will define 200 kilobyte, definitely it will use upper path, but if I will define 2000 kilobyte, this tunnel will not come up, because we don't have 2000 kilobyte bandwidth between 1.1.1 and 4.4.4. so this tunnel will not come up. Okay, so this is the basic configuration. Now question is how we will use this tunnel. So guys, use is very simple. See, on router number 1, now what I am going to do, I'm going to configure one static route for this network, IP route 192.168.10.0.255.255.255.0. Now I am going to say use tunnel 0 interface for this network. Now what will happen whenever you will ping 192.168.1.1, it will check the routing table. In the routing table there is one route, so IP route. Yes, there is one static route available for this destination. You can see here. Yes, here, and exit interface is tunnel 0 interface. So let me try to ping 192.168.10.1. See, ping is working, and router 2 don't have any path available for this network. If you want to check, I can show you on router number 2. So IP route. See, in the routing table of R2 we don't have 192.168.10.0 network, right? Okay, because it is forwarding traffic on the basis of label, right? But ping is working. Okay, so this was the small configuration of MPLS traffic engineering. Today we understand how to enable MPLS traffic engineering on routers, and then how to create the tunnel and how to use the tunnel, right? Let's say R4 have one more network. R4 is connected with one more network, that is 192.168.20.0/24. I want to use tunnel 0 for this network 192.168.10.0. I want to use tunnel 1 for lower network. So again, what I can do on router number 1, I can configure one static route, IP route 192.168.20.0 255.255.255.0, and I can say what exit interface as tunnel 1. That's it. Like this we can use this tunnel. Okay guys, that's all for today. If you have learned something from this video, please hit on like button. If you have not subscribed the channel, please subscribe the channel guys. We will meet soon in next video. Till then, stay safe. Bye bye. That's all for today. Thanks for watching.